All right, let's talk about something you've probably seen 100 times. You've got a perfectly good party balloon, you take it outside on a cold day, and suddenly it looks a little sad. Well, today we're going to get into the science of exactly why that happens. And believe it or not, it all comes down to a really cool fundamental law of physics. You know the scene, right? Inside, where it's warm, your balloon is full, it's bouncy, it's ready to party. But the second you step out into that chilly air, it just seems to deflate. So, what's actually going on here? Is it magic? So, the pattern is super clear and always the same. Warm air means a bigger balloon, cold air means a smaller one. And it's definitely not a leak, so what in the world is causing this change? Well, as cool as it looks, it's not magic at all. It's actually a beautiful, real-world example of a basic rule that explains how gases work. It's physics in action. And here it is, the solution to our mystery. Charles' Law. Fun fact, this law is named after a scientist and balloonist named Jacques Charles. Way back in the 1780s, while working with hot air balloons, he figured out that there's this perfect, predictable connection between how hot a gas is and how much space it takes up. Now, for Charles's law to do its thing, there's one really important condition. The pressure has to stay the same. And a balloon, it's the perfect example. That stretchy rubber skin expands and contracts just enough to keep the pressure inside pretty much balanced with the air pressure outside. This creates the perfect setup for the law to work. So, okay, we know Charles's law connects temperature and volume. But why? Why does this happen? To really get it, we need to zoom way in, like all the way down to the tiny particles bouncing around inside that balloon. It all boils down to energy. When you heat up a gas, you're basically giving all those little particles a shot of espresso. They start zipping around faster, crashing into the inside of the balloon with a lot more oomph. To keep the pressure from building up, the balloon has no choice but to expand, giving those energetic particles more room to fly. And of course, the opposite happens when it gets cold. They slow down, hit the sides less, and the balloon shrinks. All right, so physicists and scientists, they love to describe these beautiful relationships with math. And luckily for us, the formula for Charles's law is actually pretty simple and elegant. It all starts with this. This little symbol just means is proportional to. So V is proportional to T. Think of it this way. Volume and temperature are linked. They're best friends. If one goes up, the other goes up. If one goes down, the other goes down too. They move together. Now, to make this a real equation we can use, we just add a constant, which we call K. You can think of K as just a conversion factor that connects the two. It depends on things like how much gas you have and what the pressure is, but it lets us turn that general idea into a specific, workable formula. And this is the most useful version of the whole thing. It lets you compare a gas in two different situations. V1 and T1 are your starting volume and temperature, and V2 and T2 are your final ones. So if you know any three of these, you can always figure out the fourth. Pretty neat, huh? Okay, but before you run off and start plugging in numbers, listen up. There is one absolutely 100% critical rule you have to follow. If you forget this, none of the math will work. I'm serious. Here it is. This is the golden rule. Your temperature always has to be in Kelvin. Not Celsius, not Fahrenheit, Kelvin. Why? Because the Kelvin scale starts at absolute zero, which is the coldest anything can possibly get. It's the point where particles literally stop moving. Since Charles's law is all about that particle energy, you have to use the scale that starts at zero energy. It's the only way to make the math come out right. All right, we've talked about zippy molecules, we've looked at the math, so when you boil it all down, what's the one simple thing you really need to remember from all of this? It's really just this. As long as the pressure stays the same, if you make a gas hotter, it takes up more space. Heat it up, it expands. Cool it down, it shrinks. That's it. That is the entire secret behind our sad, shrinking party balloon on a cold day. And that just leaves us with one final thought. We figured out what happens when the pressure stays the same. But what if it doesn't? What if you put that balloon in a steel box where it can't expand, and then you heat it up? What happens when the pressure is allowed to change? Well, that's a whole other story